So even if you aren't a huge Pink Floyd fan, many of you will be familiar with the iconic album cover of the 1972 Pink Floyd album, Dark Side of the Moon. On that album cover, you have a prism, right, like this. And in that prism, it shows white light coming in, okay, and going through the prism. And on the way out, you see this spreading out, this kind of really pretty spreading out of all these different colors. And lastly, you have like red and violet. These aren't perfect, but you get the idea, right? Basically, a rainbow comes out on the other side of this prism, okay? Now the question is, why does this happen? And to understand this, you have to understand this concept of dispersion. So this is what happens with a prism, or anything that separates lights into its various colors, like a rainbow, okay, is this concept of dispersion. And the reason why this works is, ultimately, this is a refraction problem, right? You have light that's entering a new material, and it's beginning to separate, and then it enters another new material, air, goes from air to glass to air again, right? And every time that it happens, it's even happening inside of here a little bit, right? The beginning of it is starting to happen over here, right? Then you get this separation of light, all right? But what's happening, the reason why this happens is because the index of refraction is actually a little bit different for every wavelength of light, okay? The whole reason why a rainbow happens is because the index of refraction is different for every wavelength of light. And so if you're running with this equation, right, if you're using this relationship, then if I change N2 for different colors, then my theta 2 changes, right? And if these angles change, you get this beautiful spreading out effect of the light, okay? So let's prove this. I mean, I don't want you to take my word for it, right? So if you go to the next slide that says proving dispersion, it says, let's assume that the prism in the Pink Floyd logo above is made of glass. For standard glass, the index of refraction for red light is 1.509, and the index of refraction for violet light, they're on the opposite ends of the spectrum, Roy G. Biv, red to violet, is 1.521. If white light is incident inside the second wall prism at 40 degrees from the normal, then what is the difference between the refracted angles of the red and violet light? Okay, so let's start with the question of the red light. Okay, so we have red. Okay, and I'm going to use this relationship. So we have, in this case, we're going from the glass to the air, right? And so that means that if, this is glass, and remember is 1.5 roughly. Well, it's roughly 1.5, but it changes for every wavelength. In the case of the red light, it's 1.509 sine of, it says it hits the second wall at an angle of 40 degrees, so that's sine of 40, right? And then on the other side, we have air. So this is glass, we have air, and air is obviously about just 1, right? So then we have 1 times sine of whatever the second angle is, okay? And if I solve this for theta 2, I get a value of 75.92 degrees. Pretty basic, right? Okay, that's with red light, where red light has an index of refraction in glass of 1.509. All right, what about blue light, though? Okay, let's do the same thing with blue light. So we have blue light over here. We're going to use the same relationship, except blue light, it says, this is actually violet. Come on, Snumbach. This is violet. And it says violet light has index of refraction of 1.521 in glass. So in this case, this index of refraction here is changing to 1.521. And same angle, it's hitting the glass with the same angle, this surface right here. And it's still both going out into air, which is index of refraction of about 1. And we have sine of theta 2. If I solve this equation for theta 2, I get a slightly different angle, right? The theta for violet, so this is theta for red light, and this is theta for violet light. And for violet light, I get 77.87 degrees, okay? That's not super different, but it's different enough to separate, right? This shows you that your red light is not going to bend as much as the violet light, right? So this also explains why red is like, you know, you can actually see it in the picture on the slide here. Red is on top because it bends a little bit less, and violet is all the way at the bottom because it bends a little bit more because of these different angles, which ultimately happens just because each frequency of light, each wavelength of light, gets to have its own index of refraction for any material, okay? You know, where else do you see this? Well, I gave you here in the next slide the classic example of rainbows. The way a rainbow works is that each hanging water droplet in the air acts like a little miniature prism. So you can almost think of all those raindrops or water vapor in the air when you have a rainbow as being this combination of millions and millions of little prisms that are all doing this at the same time, which, as you can see in this video, creates this overlapping collective effect that we love to see as that beautiful arc across the sky. Okay? This also explains why it is that the sky is blue during the day, but we get these beautiful reds around sunset. And that is because blue and red light have different wavelengths, different indexes of refraction for the atmosphere, okay? The atmosphere basically acts like a little lens, acts like a little prism, right? And so blue light bends more than red light. So during the day, blue light gets to be scattered to the surface, right? Because the angle is right. But at night, the sun is on the horizon, and since red light bends less, that is what is going to end up hitting our eyes. And it's kind of cool. You can kind of see an image of this happening over here in this picture, in this slide. One of the really neat things about physics is so many of the little tiny magical things in life that we kind of take for granted. Maybe we don't take them for granted. Maybe we're like, yeah, we love a beautiful sunset. Maybe we're like, yeah, I love rainbows. But there's a little added bonus when you study physics, and you're able to have at least a little bit of insight as to why all this stuff happens, okay? So now next time you see a rainbow, you can kind of enjoy the wonderful little thought of there being all these suspended little beads of prisms in the air, right? And when you see a beautiful red sunset, you can be like, oh, the index of refraction of red light is perfect such that that wavelength is what's actually getting refracted into my eyes during the course of that sunset. And it's a great conversation starter too, okay? I suppose I should end here with one little fun factoid, and that is this idea of redshift and blueshift, okay? Now, last semester, we talked about the Doppler effect for sound, right? That's like this thing where, you know, if you're a vehicle and you're racing at some speed, right, and then laying on the horn, let's say, or having a siren, so here's your little car, right, and then you're laying on the horn, and you're moving this way, but you're emanating these sound waves, so you have this cool effect where the sound waves, the frequency, the wavelength here is low, so low wavelength, but frequency is high here. So if you're on this side of the car, you hear a higher pitch sound, but on this side, the wavelength goes up and the frequency goes down. So you hear a lower pitch, right? So the car passes by and it's like, meow, right? You've all experienced that at some point. The same thing happens with light, all right? As cool as that sounds. So if you have something giving off light that's moving away from you, you see a lower frequency, in other words, a redshift over here, right? So things that are moving away from you look slightly redder, okay? You have to be going very, very fast to actually notice these effects. So if I'm just jogging away from you, you won't notice this, right? But something that could potentially be moving very fast, like stars or galaxies, these things will have a redshift when they're moving away from you. And things that are moving towards you, it's kind of bunched up, and you have lower wavelength, higher frequency, which is the blue end of the spectrum, so you get something called a blue shift, okay? And so the cool thing about this is this fact actually led astronomers to the crazy conclusion that the universe is actually expanding, because so many of the galaxies that we see when we take like pictures of the Hubble telescope, so many of these pictures that we see are actually redshifted, right? So the only explanation for this redshift would be that these galaxies are moving away from us. So nearly every single galaxy that we see when we take a picture is shifted slightly to the red side of the spectrum, which implies they must be moving away, which implies the universe must be expanding. And this led to some wild breakthroughs in astronomy, including the insight that the universe isn't just expanding, but it's expanding at an accelerating rate. In other words, things aren't just moving away from us. They are racing away from us and getting it faster and faster and faster, which is bizarre, right? We have this gravitational force that should be shrinking the universe, should be like bringing everything back together again. But instead, we're seeing things like being pulled apart. It's almost as if you were shooting a basketball, right? And then suddenly, on the way to the hoop, it grew rockets and started shot over the basketball hoop by like 10 miles, right? Bizarre. You wouldn't expect it. This is one of the reasons why astronomers had to acknowledge that there might be something called dark energy out there, and that we better try to figure out what might be that thing called dark energy, and help us actually understand what might be the ultimate fate of the universe if it's actually not just expanding, but expanding at an accelerated rate. I hope there was a lot of fun, juicy food for thought in this week. And with that, I will see you next week.